Hi, Kristen. Hi, Janice.
Hello.
Yeah, nice seeing you connected.
Nice seeing you.
Did you get the email with slides?
Yes, I did.
Okay, very good. Hello, you. Nice seeing you connected. How things are going in the web? Is everyone allowed to come to the work, or it's still yet on the distancing?
My colleagues already come back to work. Han says maybe I can come back to work this week.
Okay, okay. So let's wait. We will get Mahima and Joyanta to join. If they don't, in a couple of minutes we'll start anyway. I didn't share yet the recordings. Oh, hi Joyanta, nice seeing you connected. So I haven't shared the recordings of the last meeting, but it's on the way. The file is it's bulky information with high resolution, and it will be available very soon, maybe before we end today's meeting. Um, okay, I'm starting to share the screen. So I believe this figure will make you a bit happy.
But I don't find the DNA built up in the Avogadro. I only find the Nanotubes.
We will discuss it. We will discuss it during the practical side. So, as in previous days, I will go through some equations, and you do not need to involve yourself full time in it. The promise was that the course in the summer will be mostly on practical aspects, but it will be very hard, at least for me, to go over practical things if you do not get terminology. So please tolerate it, and I'll show some slides, and then we'll go to practical aspects. Let me copy this link. Copy. And I'm going to share it with everyone once again. So many thanks to Janice for selecting choices, and Joyanta, if while we are while I'm verbalizing the lecture material, please try to go into this link and check if there are empty subjects that no one did sign up, and decide if you want to try presenting it next week. It's not like if it is impossible to pick up material, do not worry, but if you try, would be great. And this link is Google Slides, I think. So if you follow the link, you'll see that you are able to edit. So just place your cursor near the subject that you could be interested to present and type your name. So, okay. So this is a summer course in computational chemistry. There are a couple of books that partially cover things that we are doing, and the materials in the practical aspects and in lectures are symbolically chopped on 4 pieces. So right now we are in the first chapter of molecular modeling, and the practical goal is to analogous to experimental synthesis. Like in experiment, there is synthesis and characterization. And what we are doing right now is, to some sense, is synthesis. In the theoretical part, we are covering some background, and I should give some disclaimer. The equations now are much more harder than in the next chapter. So as soon as we already covered most heavy theoretical material, the Born-Oppenheimer approximation, and I'm happy that everyone was, or most of you were on the connection last time when we covered Born-Oppenheimer approximation. All things after that will be in some sense easier, not as challenging. The goal of this theoretical complementary part, before we return to practical aspects, is to explain ideas behind geometry optimization for the models that we build. So today we will cover Ehrenfest theorem that helps to go from quantum properties of nuclei to classical properties. So a little bit more details on what we discussed at the end of previous theoretical lecture. And on Monday we will discuss algorithm, the flowchart, how the computer code optimizes and finds optimal geometry. And then on Wednesday there will be presentations in which all attendees of the course will share practical skills related to building molecular models. So it is what I saw on this link, Google Docs, when I was checking it 5 minutes before our meeting. And I do not see Mahima for the second meeting in the row. She's still registered, but just in case she will have less enthusiasm, Jayanta, you may check if aspects, if the subjects selected by Mahima could be, and not checked by anyone else, could be of interest for you. If she comes back and presents, then you'll have a little less load than Mahima and Jayanta. If no, we will have all materials covered. And I believe I did send presentation materials from previous years with everyone, maybe except Jayanta. So I need to resend these materials to you so that you can use it for inspiration for next week. Also, there is homework number 3 that shouldn't be, all things we are doing here informal, so do not worry. It's quite easy thing, and if you decide to do it, it will take maybe, I don't know, 20 maximum 30 minutes. And for the practical part of the homework that I'm going to explain, we will start doing it today in the practical session. So to make it not scareful to just immediately to go to a practical thing, the homework will have two parts. One practical side of building a hybrid model with heterogeneous, with combination of two heterogeneous objects in one atomistic model, and I'll chat a bit about it more, and we will start doing it today. And the second part will be more theoretical, looking online into Google and maybe make one slide explaining concept of potential energy surface. So I will return to this image later. The practical part of the homework includes building model of so-called carbon nanotube, and you do not need to know what it is. We will discuss it, and some of you are well familiar with it. For some of you, it's kind of new material, but from practical side, we will follow very easy steps. So it is a nanostructure made basically of carbons, and then build model of oligomer of DNA, and then combine both models in one simulation cell. And the idea is for each of these three cases to optimize, preferably with Gaussian through Gauss view, and find total energy. And then after one finds total energy of the nanotube, total energy of the DNA, and total energy of their hybrid, one can subtract the largest one minus two smallest one, and this difference in energy is one of the important experimental observables. This is a measure of stability of the hybrid. So if the subtraction will be negative, if this combined system, when they both are combined, has smaller energy than energies of standalone things, it means they attract together and are stable. The model is a little bit complicated, but I think it will be a good practice, and later on some of you may use it for your research aspects. And for theoretical part, you may copy paste expression for non-adiabatic coupling, maybe list examples of systems when non-adiabatic couplings can be neglected. So basically it's any room temperature frozen object, but try to be specific. And in addition, we are covering the concept of potential energy surface. This concept is critical for finding optimal geometry. In some sense, finding optimal geometry is browsing on along this potential energy surface and finding minimum. Our Monday meeting will be focused on this with all details, and it would be really great if everyone can look online into Google and find some graphical examples of potential energy surfaces. Graphical examples of potential energy surfaces, and just write maybe one line of definition. Do not waste more than like 4 minutes on that, but if you try just to think and look online for it, look online for the subject, it will be much more efficient in the continuing parts of the course. So about carbon nanotubes, it's not a course on them, and we just cover practical sites. So there are several builders, several computational tools to build nanotubes, and one of the simplest builders is inserted as a part into Avogadro, but also one can download standalone builder code on the local computer and run it. But another option that makes everyone to feel independent is to check the website on this link, that one selects parameters of the nanotube, clicks generate, and it just generates the input file. So we will go over it during the practical part. So it's here is example how the screen looks like after I click generate on this previous website. So it's top part. So it generates a list of Cartesian coordinates, and then one can combine it with short DNA strand, not infinite but finite. So finite polymers are called oligomers, and one can place them together by copy-paste option in one simulation cell, and then optimize and find total energy. So before we go to the new material, I would like to briefly recall what we did in the previous meetings from the theoretical part. The practical parts are not possible to review in brief, although we will try to do it next Wednesday. So the course includes 3 components. The lectures are theoretical background, basic equations that are inside, that are programmed in the computational chemistry software, and main part of the course is to get skills to build models and compute properties, characterization of the models by using correct software and correct hardware. And then upon computing observables, one is comparing them with experiment and communicates to peers and colleagues, which is a part of scientific communications. So when we just started this theoretical part, we set up a question: what is a molecule from the point of view of computations? And the molecule is a set of positively charged nuclei, ions, and set of negatively charged electrons. And if you want to practice quantum theory to describe their properties, one needs to be certain and have coordinates, 3 Cartesian coordinates for each ion, 3 Cartesian coordinates for each electron, and then formulate operator of total energy, so-called Hamiltonian, which will include kinetic energy, energy of motion, and potential energy, energy of Coulombic interaction. So the charges of the particles of the same sign repel, particles of the opposite charge attract. And this is modeled by 1 divided by distance between particles, with plus sign for repulsive interaction and minus sign for attractive interaction. And those are not very complicated but lengthy equations. And if one carefully takes into account all contributions to the total energy in a molecule, there will be symbolically 5 terms. 2 terms for kinetic nucleus, kinetic electrons, and 3 terms for potential. Attraction of electrons to nucleus, repulsion of electrons, and repulsion of nucleus. This problem is to find wave function and total energy of such total energy operator is quite challenging because number of independent variables is excessively high. So one tries to find approximations which allow to treat electronic and nuclear degrees of freedom, electronic and nuclear coordinates separately from one Schrodinger equation for all coordinates, electronic and nuclear, separate equations for electronic and nuclear. And we did followed the idea of Bohr and Oppenheimer, and we have stolen 3 terms of the Hamiltonian that do relate to electronic degrees of freedom only: kinetic, repulsion, and attraction of electrons to nucleus. And when we solve for this partial Hamiltonian and find electronic orbitals phi, we plug this solution back into total equation for Schrodinger equation, molecular Schrodinger equation for molecular Hamiltonian, and we make an effort to get rid of electronic wave functions phi and keep only nuclear wave functions chi. And we were very successful in all terms except the first one, which treats kinetic energy of nucleus, because kinetic energy operator is second order derivative for positions of nucleus, and wave functions of electron parametrically depend on positions of nucleus. So if we carefully process this term, top line in this molecular Schrodinger equation, we call the upper term the so-called non-adiabatic coupling plus a pure kinetic energy of nucleus. And this non-adiabatic coupling, which is a reflection, it reflects response of electronic orbitals to shift in positions of nucleus. And if one carefully processes these equations in the first term, it also includes momentum of nucleus. And this interpretation is very important, because if momentum of nucleus is zero, if nucleus are not moving, then this problematic non-adiabatic coupling drops. It will be zero, no matter how sensitive electronic orbitals are to change in the positions of nucleus. So according to Bohr and Oppenheimer, one removes non-adiabatic couplings unless we describe combustion, plasma, high photo excitations, and non-equilibrium transition phenomena. For most regular chemistry at room temperature and below, for anything frozen, for all static properties, one can drop non-adiabatic term. So then one needs to focus on the nuclear degrees of freedom and Schrodinger equation for nuclear degrees of freedom, and then one looks that nuclear wave function, which is probability that interatomic distance has certain value, and if the interatomic distance increases, this probability quickly drops, or if it contracts, it quickly drops. So one can approximate the nuclear wave function as very sharp delta function distribution, which means instead of all details, one needs to keep track only on the average bond length. And there is a temptation to speak only about average bond length instead of nuclear wave function. So from molecular Schrodinger equation, we did remove electronic part and went into time-dependent molecular Schrodinger equation for nuclear wave function, which is time-dependent. Here's time. And we are making an attempt to approximate this nuclear wave function as Gaussian wave packet with infinitesimal, with infinitely tiny width. And this is what we are going to progress through. So another thing related to the homework for Monday is definition of potential energy surface. So in both cases, if you look on the time independent, okay, we already have time dependent Schrodinger equation for nucleus, it does have regular kinetic term and two terms for potential energy. One is regular repulsion between nucleus, and another is a contribution from electronic interaction, electronic eigenstates, total energy of electronic subsystem at certain nuclear position. And if we add together these two things, it will be mu potential energy in actual molecules. So it's not only Coulombic repulsion of nucleus, but also attractive part. And if you have chemical background, you will probably buy this argument, since when there is an electronic density between nucleus, when it forms like shared electrons, bonding orbitals, this electronic cloud between ions attract both nucleus to it and forms covalent chemical bond. So this term, which we call here E sub B of R, is partially related to this covalent bond, to this bonding orbital, when a shared electron density is between atoms that are being bonded. And this term, each of this depend on positions of nucleus, uppercase R. This is called potential energy surface. And this is the key part of geometry optimization, since we need to explore this potential energy surface for all possible interatomic distances and find at which interatomic distance a system takes minimal energy. So it is where we stopped last time. Okay, today the goal is to carefully repeat some details of this transition from nuclear wave function to positions of nucleus, and prepare our next meeting where we will consider algorithm for finding optimal geometry. So Kristen is, I guaranteed, because Kristen is certified expert in physical chemistry and is aware of the so-called Ehrenfest theorem, the transition from quantum to classical regime. Janice will cover this subject in the fall semester if plans will not change. And today we will briefly go over this material, not at the level to like prove things, but just to show its impact and importance to our goals of computational chemistry. And also I am very appreciating the question from you in the previous meeting, when at the very beginning she asked whether we are going to discuss the molecular dynamics. So in some sense, our goal is to arrive to equations in the lower line in the yellow box. So we need to arrive to Newton's equation of motion for expected positions of all ions, or for all interatomic distances. Most typical formulation of Newton's equation of motion is second derivative of position over time equals to the force, right, divided by mass. F equals ma. There is an alternative way of setting the same equations, which is in a yellow box. So R uppercase is position of nuclei, and I do not keep the index of which nucleus we are talking about, because there are so many of them, and even if we put this index, equations will stay the same. And uppercase P is momentum. So angular brackets means that it is yet quantum expectation value obtained from nuclear wave function. So time derivative of the expectation value of the radius position vector R, position of nuclei, over time is 1 divided by mass times momentum, which is just definition of momentum, right? I should ask it as a question. So time derivative of position is velocity, and velocity times mass is momentum, or momentum divided by mass is velocity. So this is this equation. And momentum may change if force is applied to the particle. So force is a reason to change momentum. If you are okay with this equation, you can just lean back and relax, or open your other activity in different window and just wait until I finish mumbling the rest. So the goal is just to arrive to this equation in a careful way. So as a result of our discussion, we are arriving to two different sets of equations. One equation is for electronic degrees of freedom, and I'm skipping it here, but this lowercase phi always depends on lowercase r, position of all electrons in the system. And then we discussed either time independent or later time dependent Schrodinger equation for nuclear wave function chi. Our goal is to transfer our consideration from the wave function, which is time dependent, to expectation value of position operator, which we call angular brackets R. And we need to have a force that depends on this, how much the force acting on the particle depends on its position, which will be gradient of the total energy with little adjustments because of quantum nature. And then this force is plugged into the Newton equation of motion, or Hamiltonian equation of motions, which replace Newton equation of motion. Yeah, this is just a recall of what we did. And our activity is needed in order to optimize geometry. I think we already covered in the labs, and it is from one of the previous years. So one makes hand-drawn structures and then runs so-called geometry optimization when it explores multiple possible interatomic distances, and as time passes by through this algorithm, it finds most optimal interatomic distance and comes to equilibrium geometry, which is expected to relate to the nature of a realistic situation, and in some cases can be even measured. So from something ugly drawn by a human hand, one can arrive to the thing that matches our chemical intuition and matches the nature. So in this practical goal of optimizing geometry, we are going in a cycle-wise protocol. So we have positions of ions, we compute forces, or we compute potential energy surfaces, energy for the, at this point for all these positions, and then compute local vicinity of the potential energy surface gradient and find forces. Through these forces, we slightly update positions of nucleus and get new positions. Then for new positions, we again compute total energy, compute forces, and again repeat, move the positions of nucleus again and again. And if one repeats this procedure several times, system comes to equilibrium. So we need to give more meat to these bones to discuss this idea in more details, and it is a goal for today's and Monday meeting. So nuclear wave function often can be considered as a Gaussian wave function, and if the nuclear degree of freedom is in a ground state, like harmonic oscillator in a ground state, the Gaussian wave functions is a very true eigenstate. So it's very justified. And even for several non-equilibrium states, Gaussian wave function is a good wave function. But if we take into account very high mass of nucleus in respect to electron, even proton is 2000 times heavier than electron, then width of this Gaussian wave function becomes very, very narrow, and it is quite justified to use infinite width and delta function. So harmonic oscillator, eigenstates, first state is Gaussian. Okay, so now is mostly boring part. How to carefully get to equation of motion for the expectation value of position, for the position of nucleus. This is done by so-called, there are several names for this. One name is Heisenberg equation of motion, another is Ehrenfest theorem, but they are very close to each other. So if one knows wave function, one can also make complex conjugate of it. And there is so-called Bra and Ket notations related to direct and to the Bra and Ket, with angular brackets to the left and right, related to presence or absence of conjugation. And if one just sets up the time derivative of the expectation value of any variable, then it is three functions, and one can take derivative for each of them. So derivative of first, derivative of last, and derivative of the middle. And if derivative in the middle is negligible, we have only the first two terms, then by definition of Schrodinger equation, time derivative of the wave function is factors times Hamiltonian times wave function. If we apply conjugation to each part of this equation, we are getting this equation for the angular bracket oriented in different side. And due to conjugation of imaginary unit I, we are getting different sign here. And now these two terms are plugged into the equation for time derivative of expectation value. And one agrees that into the notation, when bra of the wave function, operator, and ket of the wave function can be denoted as angular brackets from left and right. And then one arrives to Haha equation. So H is operator of energy, A is operator of observable, and here they are commuted. So Heisenberg equation of motion. Then one can replace letter A with the momentum. So I think here is the same equation, just in a better typing. Okay, if one plugs in the position of nucleus instead of letter R, then one can practice this Heisenberg equation of motion for expectation value of position, and then one needs to compute Hamiltonian and operator of position. In doing this computation, one realizes that potential energy depends on position and therefore commutes with position, but kinetic does not. Kinetic energy contains momentum operator, and swapping the order of momentum and position cannot be done for free. One needs to pay for it, and the price for it, if one swaps the order of position and momentum, is so-called commutator. So it is imaginary unit times Planck constant. So if one carefully practices it, I do not want to waste your time, but if one plugs in this commutation relation and carefully swaps orders of position and momentum, one finds that the change in time of position will be proportional to expectation value of momentum. And if one takes care of the constants, they cancel, one will get just definition of the velocity, or definition of momentum. So in terms of expectation values. So time derivative of position is momentum divided by mass. The next, so time dependence of position is momentum divided by mass. The next step is to apply the same idea for time derivative of the momentum, and if one carefully does this procedure, then one would arrive, so momentum commutes with kinetic energy but does not commute with potential energy. And if one practices momentum is derivative over position of nucleus, and if one carefully does this procedure, then the time derivative of expectation value of momentum will be proportional to expectation value of gradient of the potential energy while other terms do cancel. So time derivative of momentum is minus gradient, expectation value of gradient of the potential energy, and it is force. Interestingly, the derivative of positions of ions is not outside of this bracket, but inside, and it is called Hellman-Feynman theorem. So now we did arrive to the set of equations. So one equation is for position, another for momentum, and they are cross-coupled, so one needs to solve them together. And if one makes second derivative of the first equation, one can plug in second into the first and arrive to the Newton equation of motion. So the time derivative of position, first derivative will become second, first derivative of a momentum will become first derivative, and then we replace it with gradient, which will mean the second derivative of position of position is equal to the force. So in some sense, we did re-derive Newton equation of motion, but it is not literally the Newton equation of motion. Here it is reflection, an analog of Newton equation of motion for quantum particles. So we keep believing in the quantum nature of protons and all other nuclei, but we neglect their quantum nature as much as possible and derive equations which look very much similar to classical mechanics. So as soon as these equations are available, our goal as computational chemists is to solve them. And since we do not have, well, even if we write down these equations in radicals in mathematical sense, they will be so huge and big that it is not possible to solve them pen and paper. There are so many degrees of freedom, so one needs to solve it numerically. And numerical solutions means solving equations in finite differences, to chop any degree of freedom, like position or time, onto a discrete interval and find value of function at certain discrete value. It is what we will be doing next time. So again, as a little summary, originally we started from molecular Schrodinger equation for the whole molecule. Through help of Born and Oppenheimer, we chopped it into electronic and nuclear degrees of freedom. Now we focus on nuclear degrees of freedom. Instead of nuclear wave function chi, we are processing the expectation value of position, transition from quantum limit to classical limit, and there we have an analog of Newton equation of motion for expected position of nuclei. And when there will be time for theoretical part on Monday, we will draw flow charts and design an algorithm how to optimize geometry based on these equations. Okay. I'm done with this theoretical part, and we need to switch to the practical part. Um, on Monday, let me bring back our list. Let me bring back our list of subjects. So on Monday, I will try my best to cover anything that was not covered by now, or give a little recall. But today I suggest we will focus on more practical aspect of doing this relatively large system, and go over the application of skills that we've got to follow this thing. If anyone will experience challenges, we will debug it as we go online. So in preparation for this practical part, let me suggest that everyone opens two windows in the terminal. One on the local computer, another on the Photon server. So when you will have in the Photon server, please go to your to the directory for the course and your subdirectory. And if you do not need detailed help, try to build the carbon nanotube model, save it to the local computer, and upload to the server. For the you did ask about the DNA oligomers. We do not have time to build them over or browse through databases, so I will just provide templates which you can take, and your task will be just copy paste and merge it with the carbon nanotube. I will do the same things, and meanwhile probably I will need to help to Gianta to cover some aspects that we were doing since the beginning. Okay. So for the building nanotubes, please let me know if carbon nanotube is a new concept for you, or you are fine with it. Let me ask one by one to decide if introduction is needed. Gianta, and if microphone is not working, you have everyone is fine to type. Gianta, how familiar you are with carbon nanotubes? I do not hear. Maybe there is problem with microphone. Janice?
I'm not particularly familiar, but I know some things, I guess.
Okay.
Not too much though.
Okay. Kristen? Okay. I'm happy to. Can you just define them, either typing one sentence or maybe telling it through microphone? Just what are carbon nanotubes? Very, very briefly. rolled up sheets of graphene. Yeah, yeah. Thank you for giving this answer, Kristen. Thank you. And you, I do not have doubts. You're the leading expert in nanotubes, but can you share it with all of us? Brief definition of what are the chirality indices are. Yeah, thank you. Maybe through microphone it would be more efficient. Would you please tell what are chirality indices?
Carbonite has many distinct structures with different diameter and triangle. So we use the NM to represent this index, the pair of integers to represent distinct structures.
Okay, yep. Thank you very much. So basically, this thank you, Kristen. Thank you, you for definitions. So this rolled sheets of graphene can be rolled with different diameter, right? The tubes can be of different diameters, and the first index, the nanotubes are specified by diameter and chirality, which is angle. Like if one rolls things not rectangular but by a certain offset. And for practical reasons, we need to specify these two indices. First for diameter, second for chirality, if we want to do practical model. The nanotubes with second index equals 0 are typically much shorter, have shorter unit cells, and they are substantially easier to model. So I suggest we try 11.0, which will be around of the order of 1 nanometer thick. And another parameter that I suggest we use here is number 3 for number of unit cells. So it will be not very long, so that we can compute it quicker, and not very short, that it will be a little bit practical. But if you need to do it for the research, typically you put much bigger number here, and frequently one needs to put different number in the second cell. So if I select, so PDB or Gaussian is preferred, but I can also do basic Cartesian, type generate, and then it immediately creates a model that I can save into the local computer. And visualize to see I probably want to change extension to XYZ. So if one visualizes it, it will show the structure like that, which are benzene rings associated in the network, and they form a tube-like structure. So my next later on we can discuss of installing this JMOL visualizer on the personal equipment, but right now it is not critical. The next step is to transfer this model to the photon cluster. And here I'm giving an example of the command, but instead of Dmitry, you need to type in your names. So we do need two windows, one on the local computer and one on the photon. And please feel free to copy. Let me show what I have in my directory for today. There is a there are files called like AA, CC, TT, GG, which are short oligomers for adenosine, cytosine, guanine, and thymine. And please copy the cytosine so that we all do the same thing into your subdirectory, and try to combine nanotube and cytosine into one unit cell and optimize to any tools that are at your disposal. So I will talk one-to-one to Jayanta right now, and then I will ask if anyone has questions, and then I will try to demonstrate to do the things myself. Optimization is best to do by Gaussian, through Gauss view. Even if you do not see things on the screen, optimization will work perfectly. The merging together is possible in most software, and one can merge. If you use Avogadro, it's very comfortable to merge two objects in Avogadro for hybrid system. Also, one can merge objects without any software, just in a command line. I hope to demonstrate it very soon. But now, let me. Are there any quick questions of anyone except Jayanta? Okay, I assume there is no signals, no voice, no text. So please try to do this merger. And Jayanta, do you have your microphone or keyboard to answer questions? Hello, hello. Oh, okay. Well, for Jayanta types that no microphone, please consider to arrange my microphone for next meetings. It is we can do some quick. Okay, yeah, thank you. So, which computer system do you have? Is it PC or Mac? Like, which computer you are using right now? Which laptop or desktop? Is it Apple, Macintosh or anything else? HP and QPP. Hewlett Packard. So it's Windows. It's personal computer with Windows, right? Okay. Okay. So please consider to here in my window I'll type TOP to prevent it from closing. So MOBA X term. So please try to type in your search MOBA X term, and when you click on it, you'll see a window like that. Please confirm if you are able to get to this window in your browser. Joyanta? Were you able to maybe share the link to make it quicker, but one can find it instantaneous. It's very, very quick. Giant, I'm waiting for your feedback. Please tell if you are able to find this link, and then I'll tell what to do next. Okay, so then click onto download. And it will give the option of home edition and professional edition. So on the home edition, you click download now, and let me give a little disclaimer. It's more comfortable if you do it on your personal equipment, like personal laptop or desktop in the web. But even if you do it on public system in QBB, this software doesn't need any super user account. You can download and run it immediately, and anytime you start working, you can download and install it within like 1 minute and do anything you need for the course. So do not do professional, you need free, and after you click download, it will be a file that you click open and install, and then it will show you a black window where. So let me know when you install it and when you run the software. Then I'll tell what to do next. Did you? Please confirm if you are going to follow this way. Okay. Well, Gianta is installing and running MobaXterm. I'll quickly share the recordings of the previous meeting, which should be available by now. Stop. Share. Copy. And close. Okay, the recordings of the Monday meeting are shared with everyone now. Yeah, thank you, and for the homework number 2. Joanta, please type how far are you in installing this MobaXterm. Also, to facilitate the communications, if your computer, and it sounds like you are sitting on a public computer in a QBB building, if your computer doesn't have the microphone, there is a shortcut. The link for our online meeting can be just practiced on the cell phone. Just copy paste this link onto the browser on a cell phone, and then it will be microphone enabled. And also there is a phone number with the collaboration code that should work as well. So even if there is no microphone, we may set up a way to communicate. So I will wait for the feedback for Joanta. There is a very important personal thing for Joanta is to log into the server as a minimum task for today, for the server that everyone in the class is doing, and it should be done in next like half an hour to be able to do things necessary in the course. And I will watch for the feedback when Joanta is ready for these steps. Meanwhile, let me make a demonstration for everyone else. So, okay, it is a photon. I'll probably make an easy setup so that we do not suffer. We do things quicker. So I'm going to remove nanotube part from the model that I have pre-optimized and share it once again with everyone to demonstrate how to merge models in the command line to be independent of graphical applications. Yes? Please?
So, when I want to change the XYZ file to PDB file, I don't know.
The PDB is automatically read by Gauss view. For XYZ, one needs to modify the header, the top of the file, in order to read it by Gauss view.
Can I share the screen because I don't know?
CCC. Now I will forward. Just a second. I will be with you in a second. Okay, you. I'm ready to answer your question. Yes, please. And maybe some of you are developing a little, I wouldn't say irritation, but questions why we built so many different models. Right now we are doing synthesis, and in 3 other chapters we will do characterization. So we are preparing some models that we can analyze later. Okay, Babel.
Babel, and then I can type anything here. How can I go back to the command?
Oh, just Control C. If it's strange, it should work automatically, but do Control C. Do can you please do ls minus lt vertical line head ls space minus lt. Okay. Can you do more or head better? Head swcnt of the XYZ. Just show what is inside XYZ file. No, not swcnt head, and then the name of the file. No. Head. Type head as you already did. Yes, and now click tab. Yeah. .xyz. .xyz. Okay. It looks reasonable. Can you please type pwd? I will go into your directory and see what happens, so that I see in which directory you are. Okay. I will go into your directory, and if needed, I will share the screen. Okay, so I'm typing Babel minus I XYZ minus O PDB PDB. Very strange, very strange. I was checking Babel to work for me before the meeting started, and it was working. What can it be? Well, let's be practical and on the it is strange. Maybe let me check. Sometimes if one adds empty line at the end, it may help. But practically, we may just create PDB file with TubeGen and then forward it to the cluster. I think it will be more practical and less problematic. So let me share. I'm going to share screen, and we will return to your screen if needed later. Screen 2. Okay. So we can select PDB right here instead of XYZ and generate PDB file and save it, like file, save as, and call it like 11.0.pdb. And also, if you, I see that in your model, you already replaced terminal carbons to hydrogens, and likely you were doing it in Avogadro, right?
Yes.
So in Avogadro, you can save it as PDB.
Although, okay, maybe I just say from the other.
Yes, in Avogadro, you can, let me bring it here. You can do file save as, and you can, as a backup, save as a PDB and also as Gaussian input, Gaussian Cartesian input. And then it will be almost ready for optimization by Gaussian.
So I will open the now or the Gaussian file.
Yeah. Just as a backup, do both and then check which one is better. It doesn't hurt to create more than one file. And one can do some force field optimization in Avogadro, but and I already did it, but it is low quality and it may corrupt shape of nanotube, and so you just click on this E with arrow down and then click start, and then it goes through optimization cycle. I still do not have a feedback from Joyanta, but Joyanta will need to interact. It's for next step. I need to tell some suggestions. Okay.
So I managed to optimize both the carbon nanotube and the DNA model through Avogadro using universal force field, but I was curious, how do you want me to combine the two files and like, you know,
Okay.
how do you want me to like orient things?
Okay. Okay. Thank you for checking. Do you know how to combine them already?
I mean, I know how to put both of them in, you know, in an Avogadro window. I know how to put like both of them in a single Avogadro window.
Okay.
I just,
Okay.
I'm curious if you want me to use like JMOL or.
No. If Avogadro is very well suited for this. So you did ask a question how to orient them, right?
Yep.
So you can see it, but let's ask the opinion of you, because she's very experienced in this system. You?
I'm sorry.
Okay.
I'm working on Gaussian.
Okay.
I just my commonality is like Gaussian view, Gaussian my view.
Okay. Very good. Do you, right now, or maybe in few minutes, we need your suggestion on orientation. I'll try to do my own, but your opinion is valued.
Oh, by the way, where's the CNN file? Sorry, I'm
Oh, yeah. I will show it. I will show it in a minute. I will show it in a minute. Let me quickly answer to Janice, and I see message from Kristen. Yeah, it's fine if you cannot answer. If you can listen, is good, and I'm trying to record and share it later. So Janice is asking how to orient. So the strand, the direction of strand of DNA may go wrap around the tube. So it will be like thread when you wrap thread on some cylindrical object. This should be most relevant, but one can also try different orientations. The only thing that the DNA should interface the surface of nanotube rather than edges. The edges are non-physical, and also if you see, if you listen what you was telling, and what if you see what I have on my window, the terminal carbons are replaced by hydrogens. Right now we are not doing infinite periodic nanotube, but short segment, and in order to avoid dangling bonds, we put hydrogens at all edges. Is it enough? Does it make sense?
Yeah, that all makes sense. That's perfect. Okay.
Okay. Now, I will answer the question of you. So copy. Lab6, and here you just select what you think is needed. Like everything that starts with CCC into your directory, and let me just check which one is the best. CCC opt1, yes. Opt1 XYZ into here. So I did copy the 3 segments, oligomer of 3 cytosines into your directory, and I think it is answer to your question.
Also, I have another question.
Please.
So when I open the calculator with the W and I try to follow the same calculation as you told us, but it says it needs some error for the input.com file.
Okay, okay. I will arrive. Let me do the things myself, and then I will check. I will show what I have, and then we will compare. Log check. Com. More svct dot com. Connectivity. Okay, at least it starts normally. I'll explore and check, but it will take me a little time. Thank you for bringing it up.
And another question is for the CP comment. So how do you copy one file to another location? Because I'm looking at copy.
Okay, I already did it. If you look into the chat line, so I'm staying. I did cd into your directory. It is what I'm showing. pwd. So I'm in your directory, and then I did so this double dot means go up one tree of directories, or alternatively one can do, instead of this, let me quickly.
We have a
Huh?
repeat the dot 2 times.
Yes. Let me explain. This is much easier question. So if I go into cd, Ctrl C, Ctrl V, I will be in my directory, right? So without tricks and shortcuts, I would do copy full path to my directory, name of the file that I want to copy into your directory, and then wait. So here is a little bit boring but absolutely correct format of the cp command. So you type cp space source space destination. But often it can be, if you are using neighbor directories, you can use this double dot syntaxes, which means just go one ladder up, one ladder closer to the root. If you need one more ladder closer to the root, you do it once again, and then you return back to where you need. So you go from CNT to U, then double dot you get from U to CHEM676 summer, and then you type Dmitry, and then you type lab6. So you go on ladders up and down. I still do not have feedback from Joyanta, but I'm waiting for it. Okay, so I'm going to go back to my directory and try to merge two files without Avogadro, without Gauss view, just in a command line. So, okay, variable input cmt110.pdb minus o xyz xyz. Okay, I have a model without carbons, but so I'm going to combine two files into one. So I'm typing cat, which is concatenation. Then I do C, name of the first file, and type bigger, and I can call it hybrid dot xyz. Then I do cat, name of the second file, ccc underscore opt xyz into now. If I look, let me copy paste this command into common chat. Also, we may need a little bigger font. Okay, that should be better. So I'm copying these commands into the common chat. Now, if I look what was at the beginning of the carbon nanotube file before I merged them together. So it was 132. What was in the beginning of the cytosine oligomer? 90, 90. So 132 and 90. So by the format of the XYZ file, the first record in the first line should give total number of atoms in the model. So if I blindly merge two files, this operation in command line, this operation is not done. So I need to add together 132 plus 90 should be 200, 222, 222. So I need to modify the first line this way. So also, if I look to this onto this hybrid, it is at the beginning, it shows portion for carbon nanotubes, and if I go through, then it shows portion for the oligomer. So it's two segments. I can improve it by doing a command of sort hybrid into, let's say, hybrid 1. So if I do head hybrid 1, it shows that there are 132 and 190. I want to modify it, and VI hybrid 1. So I'm putting I for insert mode to 222, and then delete escape dd dd escape colon right quit. Let me look on this hybrid once again. So I look through. It looks like all carbons go first, and then there is something that I do not like. It tells not the Cartesian coordinates, but heritage from previous steps. It tells like CNT energy. We do not need this record here between carbons and hydrogens. So I want to find this place and erase it. So I'm opening VI, going to this line and deleting it by typing dd escape colon right quit enter. Let's do more hybrid 1 once again. So at the top, number of atoms, empty line, then coordinates of carbons, coordinates of hydrogens, coordinates of oxygens, and 3 phosphines. So it looks okay. It looks okay. And if I want to practice it in the Gauss view or Avogadro, I can try Babel, if it will work. I can try Babel minus input x, y, z. One output PDP. Let's check if hybrid if Babel will work on here. Yeah, maybe it's same thing as you has noticed. By converting from XYZ to other formats, it has some challenges. What can I do then? I do Control C, and I have two options. One is to open it on either Gauss view or JMol on the cluster, or I can download this file back to local computer and explore there. which could be quicker. So on the local computer, I just copy everything what is in my today's working directory on Photon. And exploring this hybrid one. So it did put together, just by merging coordinate files, it did put together these two models into one simulation cell. And in JMO, there is an option Save As. .tdb. Or now I can close it. Or I can do the same in Avogadro. So file open. Open XYZ that was created manually. Hybrid one. Open. It's still thinking. It's it tells me in other window reading multi-molecule file. This may take a while.
What does the sort command
mean? Sort means arrange according to it just sorting. So if you make a file of 3 lines, first line will be 2, second line will be 3, and last line will be 1, and call it like test, and then you type sort test, it will reorder lines and make it 1, 2, 3. So and it applies both to numbers and letters. So if you make this file consisting of let me make a little demonstration. So if I type vi test and type like b a c 3 d, something like that, and then escape, right click. So more test 1. It has this strange thing, and if I type sort test test 1, it arranges like 1, 3, A, B, C, D. So it arranges according to numbers and letters. Make sense? Okay. Thank you. So in the Avogadro, it did read this combined file that was obtained by merging carbon nanotube and this fragment of DNA. And I will forward it to the Gauss view and optimize, but before I want to do the same what many of you have already done. I want to replace terminal carbons to hydrogens. So I will select this builder and click on each terminal hydrogen, terminal carbon to change it to the hydrogen. No, I don't think this one. Edit. Update. Okay, all terminal atoms are replaced from carbon to hydrogen. And now I'm going to save it. File save as. And I'll call it maybe hybrid 2. And call it Gaussian Cartesian input. Okay. And just in case, I'll save it on several other formats. Maybe as PDB. And what else it has? Okay, and let it be also Gaussian Z matrix. Okay, so now I am transferring everything I have in my working directory on the local computer onto working directory on Photon. And now I'm going into Photon. Okay, I was not disconnected. And I have hybrid 2. Yes. And I type Gauss view. Oh, okay. Can I connect X server? So I need to log off and log in with graphical tunneling mode. Copy. Exit. And then I need to type SSH-Y to enable the graphical connection. Okay, browse view. Okay, it plays picky on me, so it doesn't want to recognize word.go. So I'm making copy hybrid to GAU into hybrid2.com. Okay, it doesn't look, it's not so bad. Okay, now I'm trying to open it once again. File. Open. Mm-hmm. So it's unhappy with something, but it offers to view the file. Now start over and just open the PDB. That should, it's quite universal format and is expected to be readable. To PDB. So it did read this model created in three fashion. So the model was built by downloading, creating and downloading Nanotube from the database, merging it together with oligomer in the command line, and then resaving in the reasonable format, converting from XYZ to PDB in Avogadro. Now I can try, if I will be lucky, to check if there will be any errors or no in optimization. So file, Gaussian calculation setup. And since I already heard from you that there could be some problems and difficulties, I want to be on a very safe side, and before doing optimization, I will be like crazy cautious. So I will do the energy only first. So not optimization, but energy. Of course, I do not want hard to fog. I will do mechanics, UFF, dot, and just do submit. Would you like to save input file? Yes. Let's call it hybrid2 opt uff.com. Save. Okay, it suggests to some replacements. Submit the following to Gaussian. Gaussian completed for input file. Check log. So no errors. So at least if I do not optimize and only do single point, it does something good. So it's not a solution of the whole problem, but at least something. You do you watch it?
Yes.
Okay. So we can open the resulting. So it didn't change anything. It was just looking for total energy according to UFF, and I can go into results and look for summary. So total energy, it shows in different window, I need to pull it here. So total energy, 1.57 atomic units. Okay, the absolute values are not very important, but I can write it down on a piece of paper. 157, 15, 89, 69 atomic units. Okay, now after this, I would like to start from where we stopped, from this log file, and do calculation once again. Gaussian calculation setup. One of the problems, and it is guilt only of myself, not of anyone else, that there is one oxygen missed on one side for phosphoxide group, and maybe something is missed on the other, probably hydrogen. So the number of electrons is odd, and the doublet is not the best thing to follow. It goes much better with singlets. But okay, let's select job type, and instead of energy, let's go for optimization. Method, mechanics UFF doublet. Save. Oh, previous one was just single point energy. Let's call it opt2, second optimization. Save. Submit the following to the Gaussian. Okay. It may take a little longer, although the UFF is the quickest and least. Okay, it instead of 2 seconds, it was like 30 seconds. Completed without error. It shows the log file with. Let's open. I'm very curious to see. Okay, I do not want to do three-dimensional rotations here because it's still a remote connection, but it looks like the DNA was bent a little around the nanotube, and it is very, very natural. On experiment that is done by scanning tandem microscopy, one can and from other calculations with longer models, one observes that DNA rolls in a spiral way on the carbon nanotube, and what we see here in this model, it doesn't contradict. It looks relevant to previous results. Now let's look on summary. Summary, total energy. So it shows 1.17, 59.1158 atomic units. And atomic unit is about 27 electron volts. So we get by 0.4 atomic units less So it's about by 10 electron volts less, so it's more optimal. And this number, 1.17 something, if I want to do homework myself, I need to record it and then compare it to the optimization energy of the standalone nanotube and standalone fragment of the DNA. Also, if I do not want to overuse graphical resources here in cluster, oh, you don't see it, sorry, I'm too excited and didn't put it here. Yes, here's total energy. And we discussed it last time that one can do grep energy file name.log, and then it will give this total energy in the command line. Okay, what else I want to do is to file, I want to export it. I want to save it under the PDB as more universal format. Yes, PDB. So I will save it as PDB. No, let me check different name. Once again. So just a second. I'm finishing the lecture in 3 minutes. Let's put just number 3 so it will be unique. PDB here and save. Okay, done with saving. And after that, I'm fine to close the ghost view. Let's manage MT. Okay. So we have this hybrid 2 optimized UFF, and on my local computer, I'm going to just blindly copy everything we did today in the lab into local computer and type in password. And after that I can open the resulting file. In one of the visualization tools. So I select JMOL, but it can be anything else. And it added curvature to the strand of DNA, and what could be problematic. What I would recheck if I would do this for hire, for paper, for through research. By some reason, it gives this pink atoms, and they call it H2, so a different type of hydrogen. I would replace it in hydrogen and redo, because it looks a little strange, this pink bonds and different name for hydrogen. But also, if one wants to be meticulous, one can measure distance from each conjugated ring of the cytosine base to the surface of nanotube. And originally, I was expecting it will form the pi-pi stacking between this ring and surface of nanotube, but it looks like there is a certain angle between this ring and nanotube. Okay, I think we are done for today. Please ask questions.
I'm not how you added the hybrid file.
Oh, you don't combine? Yes, I'm not insisting. Combined is better. Yes.
And then you change you added the file. It needs some line or something. I lost that.
Pardon me?
I share the screen and then can forward.
So I apologize that I was not. Oh, okay. But we will try to debug your stuff. But if things doesn't work, you can look on the files in my directory. Okay.
Okay.
So what you're showing? You're showing.
Yeah, so you need some lines, right?
Yes, I do. Let's scroll. I was scrolling everything that does not belong to name of atom and Cartesian coordinates. So if you just click arrow down and scroll through. Further, it will be about one up. No, it will be on the border between nanotube and yes. So here you see between what I see on my screen. Yes, there are 3 hydrogens on the top of the screen. Then there are 3 empty lines, 90. Yes, and these empty lines also need to be deleted.
Oh, I deleted this one line. So how Control D?
Wait, do not do anything. Let me tell. So if you do escape column Q, letter Q and exclamation sign, then it will exit VI without modifying not WQ but Q only. Q exclamation. Then it will not write. It will yes Q exclamation then and hit enter. Then it will be not saving your changes. And now repeat once again and be more careful with the. Yes, delete everything except coordinates of atoms.
Now it's in set mode.
Do type ESC, escape button. And now scroll down. Yes. Start from the empty line under hydrogens. Okay, yeah, good. Now escape, right, quit.
Do we change this number?
Yes, it should give the total number of atoms in your model. But we can do it later in next 5 seconds. Do escape, right, quit. Yes, escape, column, save and exit.
And where is the space here?
Yeah, empty line, second line should be empty.
I'm doing.
And now type WC space and the name of your file,
WC.
which means word count space, and then name of your file, hybrid.xyz. So 268. If it means 2 lines at the top are service lines, and then 266 are coordinates. So it does make sense. It means you have a good file.
Okay. So WC means.
Word count. It counts number of lines.
Okay.
So now you can open this file in Avogadro, save it into PDB, then forward into cluster, open in Gauss view, and run optimization.
Oh, okay, good. Thank you.
Other questions?
No yet.
Okay, Janice?
Not particularly.
Okay, Joanta? Okay, we'll talk more on Monday, and please feel free to send me emails with questions in between. We don't have formal. Okay, yes, Joanta, please send emails and we can schedule phone call or Skype in between to pick up. So I'm going to disconnect and upload the recordings. Hopefully everything goes well. And if you have free time, invest it into the presentation for Wednesday and for homework. Many thanks for dedication to the course, and I suggest we disconnect.
Thank you.
Thank you.